In this lecture, we discuss a space, a set that is related to the column space, and it's also related to the definition of span of a set. Okay, and so this space or this set is called the row space, and the relation between the row space and the column space is that the row space is the column space of the transpose of the matrix. So if we have a matrix A, which is in general considered to be rectangular, then the column space of A, if you may remember here, the column space of the matrix, the column space of the matrix is the span of the set of columns. In other words, any member of the column space would look like a linear combination of the columns. So it's this addition, this sum of scalar column vector multiplications. And now if we consider the column space, not of the matrix A, but rather the column space of a transpose. Here, sometimes you will see that you can say A to the sub t or A to the capital T. The important thing is that there is some symbol there, T, okay, that is, it looks like a power, so that's what we mean by transpose of a matrix. So now the column space of this new matrix, think of this as the column space of some matrix B, okay? And that being a column space is also going to be considered here the span, for example, of the set B1 through B sub. Okay, so how many columns are there? If the matrix A is n by n, that means that A transpose would be n by m. In other words, B would have m columns, right? So so long as you are careful here with the dimensions, this is the way of thinking about this new set, this new space called the row space. So here's an example. We have a matrix that has four. This matrix here, we would say that is 4 by, it has 4 rows, and it has, let's see, it has 2, 4, 6, it's 4 by 7, has 7 columns. So A is 4 by 7, and therefore A transpose here would be 7 by 4. And this is what I was calling the previous slide. This would be B, right? So here there would be columns B1, B2, B3, and B4. This would be a set of columns. And then we're interested on the span of this set of columns. A very common question would be, come up with a subset of that set of columns that is linearly independent and also spanning. So to do so, that this is basically what I was mentioning before. This is B1, B2, B sub 3, and B sub 4, right? And so the span of that set of columns is what we call the row space of the original matrix A. And from this step on, we know how we can address the property of linear independence and the spanning linear independence property. In particular, we can see that from row reducing A transpose, in this case, we have that for A transpose, we have that R equals 3. Very importantly is that, well, okay, so R equals 3, and the set of indices containing the leading ones, that set is going to be 1, 2, and 3. So we could work with columns B sub 1, B sub 2, and B sub 3. If we select these columns, Okay, if we select these columns, then we would be selecting a subset of the columns of A transpose, a subset that is linearly independent and also spanning. Okay, so if we work with this subset of the columns of A transpose, this is basically what we had done before when we studied column space. Then this subset is linearly independent and spanning, so it's what we call a basis. This would be a basis for the row space of the original matrix A. And very importantly, basically what we have done here is summarized by this theorem. Suppose you have a rectangular matrix, so the column space is always equal to the row space of A transpose. You may think that this is exactly what we just, what is new about this. What we talked about previously is that we were defining the row space of the matrix A as the column space of the transpose of the matrix, right? So the row space of A is the column space of the transpose of the matrix. And this is something that sounds very similar, but it's not quite the same. This says that the column space of the original matrix is going to be the row space of A transpose. Why is that? Well, maybe you can work out by using this definition. Then this row space of A transpose will be the column space of the transpose of the matrix we have there, which is A transpose. And if you take the transpose of the transpose, then you're going to end up with, you could read the proof of this. Okay, so I'm gonna leave this here, that with a question mark, for you to complete this. You can consult and work out the details of the proof of this, but you have some intuition.